Right, so our speaker today is Dr. Chulaevsky from France, from Reims, and he will talk about dynamical localization and many particle Anderson models with long-range interaction.
Okay. Just in time, as always. Okay, thank you, and not just by tradition, but very sincerely, I would like to thank the organizers for this invitation. I have been visiting this institute and this university more generally since almost exactly 12 years. It never gets old, it's always a great pleasure. And I will skip most of the historical introduction, except for saying that actually on these premises, in this university, and in this institute, the multi-particle version of localization theory in mathematical very tiny way was born and grew up. Okay, so let's do some. Should work.
Just click at the slide.
So,
aren't you going to comment on the first page? I thought that you were going to say
if you
something
like,
interesting.
what are the questions?
Is this an example of some trajectory?
It's a very good example of trajectory I have been following for 12 years.
It is connected. It is connected, is it?
Yeah, it's a simple path, a Jordan path. And it is connected to the top. Okay, so here is the main hero of the story. Multi-particle variant of Anderson Hamiltonian. So you could write either this way, just kinetic energy, plus the total potential energy coming from the external random field. It is random, that is important, plus the interaction. Sometimes people ask, what if the interaction were also random? It's a problem. No, any bit of randomness in localization, anyway, in the localization theory, is very, very welcome. Okay, because it's disorder. We need more disorder. Right. So another way of writing it is to take n replicas, and it's some fixed number. Okay. And by the way, it's important to say that n is not going to grow in any way with volumes which will appear. That's not really physical. It's not proportional to the volume of the system. Okay, so you take n replicas of single particle Anderson operators, Hamiltonians, acting each on its own variable, and without u, which mixes all up, of course, that you'd have separation of variables. Now you don't. Okay, who is who here? Practical example is, of course, the configuration space for each particle, and for all of them separately, a lattice. Okay, but in fact, there is no real reason to restrict yourself only to lattices. So it generalizes very easily and effortlessly to any graph of polynomial growth of balls. Okay? So just think about lattice. Even a one-dimensional lattice would be a good example, because there is no such thing as one-dimensional, even two-particle problem. If you have at least two particles, you have a Hamiltonian acting on the functions of two variables, and that's about it. So. So even if we are not on the lattice, the polynomial growth of the balls is assumed. Now bold phase letters will be usually reserved for, so to speak, multi-particle objects, and simple phase V is a random field on X, which is lattice or not, relative to some probability space, right? I take a very nice example of a random field which is IID, and has a bounded density. Okay, bounded density, and even completely supported. The complex support is more important to the technique I'm going to discuss today, a fractional moment method, that it would be for another well-known method, multi-scale analysis. But anyway, I assume the support of the measure for V bounded, and then why not 0, 1? Because anyway, we are going to multiply V by a constant, which is going to be huge, as big as we want. Okay, so this is the main scene. Now the result. Well, in 2 words, it is. Yes, okay, I did. This is basically an extension of the result. But we can report it here in this institute during the program Mathematics and Physics of Anderson Localization, 50 years after. Okay, so they treated the case where U2, the two-body interaction potential, which I suppose not to be infinitely extended, but exponential decay, they suppose that U2 is a function with complex support. On the lattice, it's just finite support. Okay. Now the result is typical for those in localization theory. You get a spectral localization, that is pure point spectrum entirely, and exponential decaying eigenfunctions. And there is also a statement about dynamical localization, again with exponential rate, which is a sort of trademark of the fractional moment method. With multi-scale analysis, you don't prove exponential dynamical localization, even for single particle, for some good reason. Okay? Here we can get both exponential. Okay, so yeah, essentially a more extended version of this is in archive. All the language in the archive preprint is 2 particle, but it's not a big deal to make the number of particles bigger. Okay. So the main problem, if you call the problem, is to extend the techniques by Eisenman and Avanson to the exponential decay interactions on the lattice.
So what is dynamical localization as opposed to?
Dynamical localization is that if you apply the propagator to any completely supported function, okay, in the continuous case, you take a function which is completely supported in O2. You apply this unitary operator, see how it propagates, and even if you multiply this, amplitude of propagation by a huge function, by exponentially increasing, you get a finite norm. This is, by the way, the norm of the function. Or if you treat this, which you can do only as an operator, this is an operator of the norm of operator. And this norm is finite, meaning that even after propagation, over any time, it is still bound. Okay. Well, I mean, it it's a bound state, despite the propagation. Now, okay, the first question, which is here, probably the first one which pops up in your mind, and it may, isn't it all obvious, given the 30 years worth evolution of mathematical localization theory, isn't it all obvious that if you take 2 particles instead of 1, even in one-dimensional space, even on the lattice, that the eigenstates should be localized? Well, sadly, it is not. And to see this, let's take the following example. Well, what's the worst enemy of localization? It's propagation, right? So what's propagation is due to? Usually due to resonances between eigenvalues, local, so to speak, local eigenvalues. I get to that in a moment. Local eigenvalues corresponding to 2 very distant loci. So we are working with a 2-particle system, and I take 2 configurations, which are sites on the graph. X with 2 particles, which I make sit at 0, and Y with 1 particle still at 0, and another one at R. Okay. These are two configurations, and of course the distance between them, let's say a normal distance, norm distance, norm distance is huge if r is large. And still, if we are speaking of local energy levels, to make it rigorous, make this notion rigorous, let's put some finite balls around these sites. And for the sake of argument, I suggest taking silly balls of 0 radius, that is single side balls. Still, it's non-empty set, right, each. And we got Hamiltonians, so to speak, Hamiltonians acting on the functions supported by one point. What does it mean? Such a functional space is one-dimensional, and any operator is a multiplication by its unique eigenvalue, right? What are these eigenvalues? Forget about kinetic energy, because there is no place to move, right? I also suggest to forget about interaction, not because it's simpler, but because it's not going to help with the problem I'm going to review. Let's take a look at these local eigenvalues. The corresponding wave functions don't know anything about each other. You just take two single set balls. Right, lambda is the v of 0 taken twice, and mu is v of 0 plus v of r. A rhetoric question: are these two random variables independent? No way. And worse, it doesn't depend on how large is the distance. Well, what we have to face here, compared to the conventional localization theory, a severe deficit of independence, or even weak dependence at distance, even decay at a large distance. Well, that was melodramatic, wasn't it? But there is such a thing as condition. So if we condition on v of 0, it's the only guy which makes them correlated, then what's left is lambda of omega, which is constant now, but mu is not. There is one random degree of random freedom here, which is alive. Therefore, the distance between these two eigenvalues is small only with small probability. If v, as we assume, has a regular distribution, the problem seems to be solved. Well, not quite. Not quite, because there is still a simple but important observation to be made. What we really used here in this simple trick, seeming to solve the problem, this instance of this larger problem, is that the two configurations, and in each fourth configuration there are particle positions, right? So there are sets capital X and capital Y with the positions of the particles. We use the fact that one particle here, the one which is at R, is separated from the cloud of all the other particles. It's a bit an overstatement, all the other particles, because only we have 4 particles here. But even with larger number of particles, we would need to make the work of this trick, we would need sort of a front runner or a pack of front runners, particles coming from the same team, from the same configuration, which are separated from the cloud of all the other participants. If they got stuck in the cloud, it's boring, and it's not going to work. So there is a word for such kind of separation. These two sets, or if you like, the corresponding configurations, are separated in the Hausdorff distance. And I'm going to repeat these words, Hausdorff distance, all the way through the talk. It's a very important player in this game. Okay, next question is, okay, there is something which probably can help us, but how useful is that? To prove even the decay, the square summable decay of eigenfunctions, let alone exponential decay, we would need some ability and decay in the genuine distance. But Hausdorff distance, and that's the catch, is only a pseudo-metric, right? So how useful is that? Well, some simple inequalities between different kind of metrics here. The norm distance, well, I'm writing the norm, of course, I mean we are on the lattice. Otherwise, I would have to use the product graph distance. It's a bit of headache. So the most traditional distance is upper bounded and lower bounded some things. But what's important here is that the Hausdorff distance we are going to work with is lower bounded by the normal distance minus the diameter of whatever point you wish, which means that you put here the minimum of the two diameters. Let's make it x, and let's fix x, and push y to the infinity. What happens? This guy is constant, so the right-hand side goes to infinity, and so does, therefore, Hausdorff distance. And why it is helpful? The proof of this inequality is really elementary. What does it say us? Well, it says that we have this inequality. Exponential decay with respect to normal distance is related to exponential decay for Hausdorff distance. No, I should probably have it the other way. Yeah. Okay. Anyway, this tells us that decays we are going to obtain for Hausdorff in Hausdorff distance are helpful for the normal usual decay. Okay. Now, we are going to speak about fractional moment method, and fractional moments, any moments, are expectations. Are they finite? That's the basic question every time to be asked every time you plug in the fractional moment method. Well, there are some ready-made results, and here it's a basic lemma one needs to use, and this lemma was put in the multi-particle context by Hasman and Watson by adapting existing techniques from single particle theory. Is that indeed, if you take green functions, raise it to a fractional power, otherwise it would diverge hopelessly. And even if you put some suitably chosen sigma subalgebra, which I'm going to discuss later, which makes the things only more complicated. The result is stronger, right? With condition. Still, this conditional expectation converges. Not only it converges, but you can get as small number as you wish by taking the coupling constant in front of the random potential large enough. Okay.
So what is F here?
It's some sigma algebra. You condition on some of the values of the potential. Okay, more precisely, you can in the single particle space, think about one lattice, one-dimensional lattice. You have a lot of points. For some reasons, which will be clear later, you may want to fix V on all of them except 2 points. It's a severe restriction of the randomness. And still, under this restriction, the expectation of the fractional power converges.
And S is between 0 and 1, or?
Right. I think it's fractional power.
Okay, it's a fine.
I should have written.
Connecting to this question now, it seems that you could take S equals to 1, right? What happens with the right-hand side if you approach with the S1?
It diverges. It diverges because for
Constant.
oh sorry.
The constant
Constant
depends
is
on
1
S.
divided by 1 minus S.
Okay.
Well, constant depends on F.
Yes.
Okay.
It's a small room. You know
Do you
everything
need
about
to-
your document.
Okay. Now, okay, so take a one-dimensional functional space, then the, so to speak, result is 1 over E minus random variable psi. Take absolute value, take expectation. For the smoothest distribution, I have an infinite expectation. That's why the moments in this science are always fractional. That would be wonderful. That's not the way it is. Okay. So, okay. What is? I probably pushed it many times, right? Okay. So, all the technical details are in the archive print, and also some of them in the PDF file. So let's get to work. Now, the things I am not going really to discuss here is how to get spectral and dynamic localization from the fixed energy analysis of the fractional moments of the green functions. For several reasons, the time is always limited, and also these kind of derivations, or look at the other way, the reductions, are well known, and there are several versions of them. Some were developed in the framework of the FMM, fractional moment method, some others in MSA. So there are ready-made tools which allow me today and now to focus exclusively on the fractional moments and nothing else. So results which I stated, will follow from the analysis of fractional moments for any fixed energy. It is arbitrary, but has to be fixed through the entire analysis, and that suffices for the proof of spectral and dynamical localization. That's the way it is. Okay, so let's skip these results. I would need at least 5 to 10 minutes to explain what is what there. And now about the structure of the proof. The first thing is that I have to mention is that there are two kinds of objects used in all this discussion. The green functions, and this is the number of particles of the respective system, and the eigenfunction correlators. So it's a kind of loop. The green functions are the main objects for the entire fixed energy moment analysis. But to get some information about the n-particle green functions, it is suggested in this method to use previously updated information about the eigenfunction correlators for the subsystems from 1 to up to n-1 particles. For example, today, since I only have a two-dimensional screen and not four-dimensional in five-dimensional space, I have to draw all the pictures only for two particles in one-dimensional case, right? So this means that the only step which will correspond to this talk will be derivation of information for two-particle systems from the information about the one-particle subsystems available already in the conventional theory. Okay. Now, this is one of the relations between the green functions and the eigenfunction correlates. By correlates, I mean psi of x, psi of y. And moreover, usually you apply expectations, sometimes you don't. Okay, so this is a deterministic statement. There is no randomness here. Okay? Because the only thing you vary in this integral is the energy. Whatever localization or delocalization you shop in the eigenfunctions is there in the green functions. And actually, I will be, so to speak, hiding the truth up to the very end. That I will put systematically expectation only with respect to disorder, with respect to the probability and measure p. But actually, most, not all, but most of the computations are made in not in the disorder space, omega, but in the product space, energy times disorder. So this is why we need expectation with respect to omega, which is omitted in this notation, from this notation, and also integration over I. Okay? To make this integral also an expectation, if you want, you need to normalize by the length of I. Let's say I is of length 1. Okay, so there is some result. It has to be proved, can be proved. And one of the key points of the proof is a remarkable Boole's identity, which is here. Usual references to the original work by Boole, which is very long and dates by 1857. The shortest proof I know of is given by Loomis half a century later, I think, and it's exactly 10 lines long. Okay, so now a big surprise, and the multi-particle localization theory is full of that. The trademark of the Eismann-Molchanov method since its inception in 1993 has always been a monoscale technology, meaning that if you get some information about the green functions in balls of some size, or let's say limited size, then you can get everything you can dream of by using only steps by fixed size. Well, it doesn't work here. And it was a big surprise, at least for me, perhaps for some people too, that in 2007-8, Michael Eisenman and Simone Wurzel made a big sacrifice, or if you like, a gambit, which they played and won, avec brio. They sacrificed the monoscale technology. So the bottom line is today that we have not one, but two multi-scale inductive methods for proving multi-particle localization. One is based on bounds in expectations, and that's MP FMM. The other on bounds in probability, and that's MP MSA. Okay, now, okay, in accordance with what I said, the proof is a double induction. There is a finite induction in n, from n equal to 1, which is a conventional theory, to whatever n you want. But you can't go to infinity, because in the beginning, you have to anticipate the loss of efficiency of your methods as you go from n minus 1 to n. Okay? So you have to get in stock enough randomness to reach, for example, n equal to 10, and much more for n equal to 20. Each step is a multi-scale induction. And I'm going to explain this induction. The first step might seem to be hard, but it is not. Okay? So there are again some ready-made results. You just adapt them easily with no effort. It works. The tricky part is scaling step. Now, if we are talking about scales, what are the scales? It is convenient to take almost a multiplicative, affine, if you would, growth. You double the previous scale, and you add a little something. Okay. Then, again, it is sufficient to prove the decay of the green functions for x and y in Hausdorff distance by some r bigger or equal to some number L0, which you are free to choose. Then, with these length scales, there is of course some k such that r is sandwiched between Lk and Lk plus 1. And now the k will be fixed for the rest of the argument. Here is some drawing which says what is going on here. Well, this is one configuration space of, let's say, for the first particle. This is another replica for the second particle. This is a very important object, the diagonal. This is where the interaction lives if it is a finite range. And, well, to symbolize that, I put dark. I think the second strip is just invisible in this Yeah, in this beam it's just invisible. Okay. Anyway, so this gray strip means where the interaction potential essentially lives. Now it is everywhere because it decays exponentially, it lives everywhere. But this is where it essentially lives. Okay? So this is where interaction is really important. There are two kinds of, let's say, I will make a rough classification, very crude classification of the particle configuration, two particle configurations. Far enough from the diagonal, away from the support of the interaction, and not far away. Okay. And we'll be playing with two configurations, x dot blue dot here, and the blue ring here is y. And like I said, they are separated by a distance which is between Lk and Lk plus 1. Now, yeah. So the first result, which is one of the steps in this scaling step, is that if you take two configurations which are far apart already, of Hausdorff distance, and in addition, at least one of them, at least one, is wide split. That means it has a large diameter. Of course, if you have two particles at distance 1 kilometer, then of course the diameter is equal to 1 kilometer, and vice versa. For 10 particles, what you can guarantee, if the diameter is 1 kilometer, is the distance for at least one pair of clouds, 100 meters, right? Diameter divided by n. Oh, no, sorry, you have to divide by n minus 1. Sorry. Anyway, this is a result which is proved everywhere outside the scaling loop, and it's fortunately it's the only place where the Eisenman-Schwarzer technique needs to be extended to adapt it to infinite range interactions. And by the end of the talk, if I ever have time, there is a sketch of the proof. Okay, let's believe in that. Yeah.
So here you have to assume this diameter assumption, right? So is this that you have to perform at least two explicit averages?
No. I have two possible situations for each configuration. Either it is far enough or it is not far enough. And all the cases will be considered. Don't worry about that. Here I say that, well, the Hausdorff separation is assumed anyway. That's the basic assumption. And the first case is that at least one is far away. If it is far away, then the Green's functions, fractional moment of Green functions, are exponentially small. That's a simple case. Okay? Before going further, a few preparation steps. Now, so we are speaking about two particle configurations, and by the homogeneity of a random field in the one-dimensional lattice or multi-dimensional lattice, you can assume that at least one of the particles in X, it's at 0, it doesn't really matter, but it matters for the pictures. Okay. Now, the Hausdorff distance between X and Y, the configurations, is lower bounded by this particular distance from 0 to one of the particles in the both-face Y configuration minus diameter of X. So we already considered the case where at least one particle has a large diameter. If it's not, then both have limited diameters, right? And now we are going to play with this upper bound for both of the diameters, including diameter of X. So in particular, we assume that the diameter of X is upper bounded by Lk squared, and if you subtract from R, which is greater than Lk, you have at least Lk over to left, even a bit more. And then another preparation step, you take this fractional moment, and using the usual result identity, y is here. They told me I have to raise the board for audience to see it. So x is here, it's not far away from a diagonal. Y isn't either, but Y is not be of much help for us because we know that the distance between X and Y is LK or a bit more, but how much more we don't know. So it may happen that if we draw a box of size LK around X, then Y may be very close. It's not helpful. So distance between Y and this boundary will be ignored. Okay? We'll have to ignore it. We're not going to make any use of it. So we are going to work with X, and by the resolved identity applied to the box of size LK over 2 around, LK around X, LK over 2 still. We get this. Well, there is a combinatorial factor, and we have a splitting of the original green function in the product of 2. From X to W, which is in the inner boundary of the box, and then from the next nearest neighbor to W prime to Y. Okay? So it's a 2-leg, well, actually 3-leg tree. From X to W, from W to WY, it's just a Laplacian. Okay? And W prime to Y, this leg is useless, but we have to make sure it is harmless. And this is where the a priori bound of the fractional moment is going to play an important role. Okay, so yeah, so now we are going to use this famous sigma algebra, knowing that W in this box, not very far from X, and the distance between X and Y is somehow large enough, at least LK plus 1. The points W are all inside the area affected by the same potential, which affects X. And we condition on all points in the single particle case, except for some of the projections which are present in W prime and perhaps in Y, but no way in X or W. So this a priori bound says that we have an upper bound which is fine. Now, next step, yeah. Okay. Now, this right place to remind, or otherwise tell for the first time, that we really need the average not only in omega, but also in the energy. And even I will omit often this superscript I. It should be put just for safety in all formulae and used in many of them. Okay. So now this picture. Okay. Now we play with X, which is fixed. Y is filtered out, and W. W makes all of the 2 around this box centered at X. Yeah. But again, W may have a large diameter and then split or not. So we have to make another loop and consider 2 cases. Either W is split, and then we use a splitting lemma to estimate the fraction between X and W. Okay. And that's the easy case. Otherwise, W is of limited diameter. And then we are finally have to play with scale. Okay. Now, the 2 kinds of eigenfunction, let's say correlators, we need is the epsilon which is here, and its version is tilde, where some of the distance are cut by half. I mean, here with L equal to LK plus 1, we divide by 2, Lk plus 1. But Lk plus 1 is twice Lk, even a bit more. Yeah. Okay. So technically we need this, but it's convenient to work first with epsilon. Now, why can we replace the required epsilon correlator by convenient tilde epsilon correlator? Because of this simple, rather boring, but useful lemma. I mean, boring is the proof. You take, you make some combinatorial analysis. You know that if a term is here but not here, it's because there is somewhere split configurations, and for a split configuration, you have splitting lemma, and you shop immediately an exponential factor. Okay. So this is approximation lemma, and now we are going to use epsilon tilde. How do we do that? Well, here is the rescaling inequality. The restricted correlator for the next scale is bounded by some constant which can be made, as you see, small with g large enough, by, roughly speaking, the square of its predecessor at the step k, but not exactly. Unfortunately, at some point, you all you can have, no, sorry. Yeah, at some step, you have to put something which is not the correlator. But this perturbation is itself exponentially small. So it's a sort of perturbed quadratic dynamics, but the perturbation is exponentially small. This is why even with this perturbation, you still get, in the end of the day, exponential decay for any sequence, uptake sequence, which obeys this recursive inequality. Okay, so there is more techniques involved, and really it takes some time. But let me say this: it's really formidable work that Michael and Simona did. Well, the entire proof, if you put aside two lemmas, which have to be put aside because they have nothing to do with the cycling or with rescaling loop, it's 4 to 5 pages. That's it. It's a formidable enhancement of the fractional moment techniques for single particle systems. Okay. Now, in the proof, if you read it in detail, you see 2 points. First, it shows you once and again why the Hausdorff distance is so useful for all these arguments. You really have to use it and not the norm distance, not even symmetrized norm distance. It's much easier. Okay? And it also shows why there is no hope now, knowing that this method is, after all, a multi-scale induction. Let me say it aloud and again. It's a multi-scale induction based on expectations instead of bounds and probability. But since the moment you get multi-scale analysis, you show some factors which are combinatorial. And these factors are polynomial here only because I assumed in the very beginning that the underlying configuration space, maybe lattice or a graph, but it has a polynomial, but anyway, sub-exponential growth of the balls and of the spheres. If you have a Kerry tree instead, with or without loops, yeah? Kerry tree doesn't have loops because of the tree. Even if you add loops, it doesn't help. This turns into ugly exponential factor. It ruins everything. Just the way it ruins every hope for the existing variance of the multi-scale analysis, single particle. Think single particle. To treat Kerry trees and any regular trees or exponentially growing graphs. Okay. Okay. I promised you an abstract recursive inequality. Here it is. So this is basically the correlator for the scale Lk plus 1. This is its predecessor it's the step k, right? And it would be squared. In which case, if we didn't have this guy, that would be a Newtonian growth, e to the power minus 2 to the power n, right? It's not. That would be, because there is a perturbation. But the perturbation, by the way, contains beta k in the power 1. It's not even a power 1 plus epsilon, it's a power 1. But fortunately for all of us, there is an exponentially small factor. I mean, it's exponentially small with respect to growing scale Lk. You solve it immediately. It's a first year exercise. I mean, so by solving, you get some upper bound for the growth, for the decay. And you see that whether it is based on the Newtonian decay of beta k squared or because of this guy, either way, you get either an upper bound by e to the power 1 exponent times lk, or another mu times lk. Anyway, it's exponential decay, and that's basically the end of the story. Okay. The story about the multi-scale inductive proof, which is employed as one step in the induction of number of particles. So it's the index space for this double induction is a strip of finite width. You start from 1 particle, go to 2, 3, up to n. And we saw how it works from n minus 1 to n, where n minus 1 were modeled by 1 and n by 2.
What happens to the?
And yet,
What happens to the disorder parameter if you go these steps?
if you raise the n, it deteriorates hopelessly. Once I made an estimate, and thank you for that question. Again, it went off. Sorry. So basically, you need a g of n as big as a to the power b to the power n, with a and b bigger than 1. You see?
That's fast.
That's yeah, enough for speeding. Ticket. What is care about this guy? Okay, what I was going to say now. Yeah, okay. I actually still have 10 minutes, right? And we started about.
You still have 10 minutes, yes.
Yeah, okay. So then I have really a few minutes for sketching the only ingredient in the Eisenman-Barty proof, which has to be adapted to infinite range interactions. Now, how it works? Okay, let's see. Yeah, this is the split lemma. So the two configurations we are working with, x and y, are Hausdorff distance. Okay, that's ground. Anyway, and now we assume that at least one of the two diameters, let's say x, is large enough. So both quantities under the minimum are bigger than some r. Then, and that's another component for the answer about the deterioration of the parameters. There is some constant c such that the green function for this split pair is bounded by exponent of r times n, which comes from the previous step, but also times c. And the truth is that c is inversely proportional to n minus 1. So basically, not only the disorder has to grow, but the Lyapunov exponent of it, multidimensional analog of it, decays factorially. Which is, I usually say that all this is a few particle localization field. With few, really few.
Density 0.
Okay. Now, yeah. Okay, this is written. Now, how we do the first? Well, first of all, it's a perturbation. It's a perturbation theory. We have, due to splitting, which is present here, a sum of two non-interacting Hamiltonians for the subsystems, plus the interaction which mixes them. Okay. The fact is that the eigenfunction correlators for this system are decaying, both for the first subcluster dimensions and for the second subcluster dimensions. And U is, well, in the Eismann-Watson proof, it's just completely supported, I mean, along the diagonal. And here it is decaying, but exponential decaying away from this diagonal. And we do some perturbation theory, which is very simple. Okay, so these are the individual correlators for the subclusters. Here for n equal to just for first particle and for second particle. Both decay in their own dimensions, right? If you take the tensor product of x1, which decays in x1, and the one which decays in x2, it decays in the plane. That's the trick. Okay. Now, yeah, and if you take the expectation of the product and the correlators factorize, they factorize, and each of them is bounded by 1. But because in the correlators, you put the eigenfunctions which are L2 normalized. And on the lattice, that means they are bounded by 1. So for the product, you take the smallest guy and you ignore the other one. Okay. Now, yeah, why the correlators are useful? Again, because we use not just expectation, but also averaging in E, the spectral averaging. So from correlators, you get an information for the fractional moments of the green functions. Now, yeah, so for the non-perturb, yeah, you have, did I write it here? Not really. I would have to write that the green functions for H is the green functions for this guy plus the perturbation. And by the secondary law of inequality, you have that. The perturbation guy is decomposed. I decomposed in two sums. In one of them, the W, yeah, what is here, by the way? You have a triple product, but U is diagonal. From X, you go to W, and from W to you go to Y, which is here. Now, this W may be close to X or not. If X is widespread, it has a large diameter, it is far from the diagonal. If X is here, it's far from the diagonal. Now, if X is here, can W, for which U is non-zero, or let's say not small enough, be close to X? No. If it's close to X, then the potential is very small. If the potential is not very small, then it has to live there, and there is a distance between X and W. And you use one of the two mechanisms and get the first and the second sum. In the first sum, U, the decay of U is of no use. You take that infinity norm of U, and that's it. It's basically order of unity. But the sum, each term in the sum is small because here the non-interacting green function is small. Because you have Anderson localization in each direction. In the second sum, W theoretically may have a large diameter, but there is a price for that. Pay with the decay factor coming from interaction. This is why S1 is small, and this is why S2 is small, because the two are exponentially small, so is the perturbation term. And unperturbed term correspond to the green functions of localized non-interacting system. That everything is small, and that's the end of the proof of the split lemma. Okay, And now, in the remaining 3 minutes, according to my watch, I can answer unasked, but potentially maybe asked questions about the decay, which is slower than exponential. Well, first, I have to highlight a recent result, February from last year, by Michael Fauser. If I understand correctly, he was or still is PhD student of Simon Vartins. Okay, in the continuous case, they proved not only decay of eigenfunction qualities for the exponential case, but also for the sub-exponential case. Okay. Well, in the if the decay of the potential is exponential, so is the decay of eigenfunction correlates, and therefore decay of eigenfunctions, which we derive by Chebyshev inequality from the bounds on the eigenfunction correlates. If the decay of a potential is sub-exponential, it only gives you sub-exponential decay, essentially modulated by that of the potential, of the potential, for the eigenfunction correlators. And since FMM is all-in game in poker, you win or you lose, or you win only from the bounds on eigenfunction correlators. If eigenfunction correlators, that is, if the rate of the dynamical localization is sub-exponential, so is the decay bounds on eigenfunctions that you get. With the multi-particle multi-scale analysis, you have more flexibility, and this is why it was a surprise for myself and my collaborator Yuri Sukhov that despite the case, despite the fact that in the case of sub-exponential decay interaction, you still get sub-exponential decay of eigenfunction correlators. For the moment, there is no way to get anything better than that. You still, by multi-scale analysis, you still prove a genuine exponential decay of the eigenfunctions, both in the discrete case and in the continuous case. And I think that is all, and I'm on time, which is another surprise. Thank you very much.
Thank you. Questions? Yes?
Suppose you take the simplest scenario. You have just two particles on Z, say a delta interaction between the particles.
Yeah.
What do you expect, and the Anderson randomness in for each of the particles?
Yeah.
What do you expect localization for all disorder parameters?
It's a difficult question. It's a difficult question because the fact that you take one dimension
Yes.
and only delta interaction is not going to help. That's sad, but that's the way it is. So a more detailed answer is that actually I didn't speak about this in the talk, and I only took the case of large disorder. But Michael and Ian Zimone considered two scenarios. Not the Lifshitz stairs, it's a different story because FMM is touchy about this, and that's why Michael Fauser and Simon Vartins did a very good job. In continuous, you have to treat Lifshitz stairs.
Okay.
But they also treated the case of very weak perturbation of a non-interacting multi-particle system, which is localized. And that's an interesting case for one dimension, as you said, because in one dimension, each particle, each localized for any disorder parameter. But to derive from it the stability under perturbations, you have to assume the perturbation is weak enough. I mean, the way it is now, you have to take G as small as you want. Lyapunov exponent is G squared times the spectral density. But you have to take the norm of U much smaller than G squared.
Okay, but nevertheless.
Nevertheless, yeah.
And
It's not completely non-perturbative. It is half non-perturbative.
Yeah, and regardless of the sign of this.
Oh yes. Oh yes.
Regardless.
Actually, I wanted to ask similar thing. So basically, if you have one-dimensional casing,
Yeah.
it doesn't matter how many particles, and you take weak interaction,
Yes.
then the coupling constant will be non-zero probably, but it will scale to zero when perturbation go to zero. Is it known how it behaves?
Which,
So,
which-
so I wouldn't expect that that you have localization for all values of coupling constant. I would expect that
I
you
would
will have
dream, yes.
certain critical value, but will tend to zero when interaction tends to zero. So if interaction gets weaker, then
yeah,
your localization
Yeah,
starts
right.
from certain
right,
value,
right.
which
I would-
also tends to zero.
Yeah.
But
I
what
would
is the
say-
scale?
I would dare say that there is a constant, absolute constant, well, more or less absolute constant, such that if the disorder parameter is G, then you get the localization is stable for the interactions with norm of U less than or equal to C times G squared. Well, maybe you have to take
can-
care of the
so-
edge bands,
So that's
of the
that's
band
the-
edges.
So what again? So if coupling constant is G, what
G
is the
squared,
size of
G squared.
this square?
Because that's the way it
So
is
I think the
for.
square root of the interaction will be the coupling constant.
Right. It may depend upon the proximity to the end, because the scaling of
Yeah.
the is different. It's one of the what's called special energies.
And this was before any number of particles, fixed number, not only for two.
Yeah, yeah, yeah. The constant which I
Constant will-
yeah.
But it's not done. It's kind of.
I don't think so, but I wouldn't say that if you look at in all preprints in some of my PhD students, you won't get something which is close to this answer. I'm not sure it is clearly written anywhere, but it may have been. It is more or less clear.
Other questions? Sasha?
I suppose that polynomial decay is a completely irrelevant question here, is it?
It is not.
Okay.
It is not. It is not, but it's a more delicate situation, and for the purpose of this talk, I wouldn't dwell on that. I mean, it's doable. It's doable.
Because in the multi-particle
And
scattering theory-
moreover,
Yeah.
there is a statement about that in the paper by Michael Fauser and others.
Okay, because in multi-particle scattering of spectral theory, the potentials that interactions that you consider here, they are, for all practical purposes, just compactly supported.
Right.
But I understand that this is-
You're correct. But let me make the following remark. As show some of the results here, the decay of eigenfunctions may have nothing to do with the decay rate of the potential. It may be much faster. For example, exponential, even if the exponential interaction potential is not exponential. However, in the eigenfunction correlators, you also have probabilities, and probabilities are a nasty habit to scale not the way you want them.
Okay.
So they assume large enough power of decay, right? You mentioned that.
What is written in the paper is a sub-exponential decay.
They mentioned that they can do also power decay. You said.
No. They say in their preprint, right? So it's a theorem in their preprint. I'm not sure it is published yet, but maybe may have been. But even if the interaction potential decays polynomially, the eigenfunction correlators, which they get from the multi-particle FMM, is sub-exponentially decaying. But it's more delicate argument, and that's why I'm not going to discuss it. Sub-exponential is much easier, and you can do it easily with multi-scale or FMM.
Other questions? Okay, let us thank the speaker again.